AT&T is disclosing yet another major data breach. The company says a third party illegally downloaded call and text records for nearly all of its 109 million customers.
This morning, consumer advocates are sounding the alarm about a massive data breach that could impact billions of people.
The information that was stolen includes social security numbers, potentially leaving millions of Americans vulnerable to cyber criminals.
OpenAI was hacked in April of last year and never disclosed it to the public.
So how does cloud security affect the average person? Well, today we entrust pretty much everything to the cloud, much more than you may realize. Legal documents, financial records, personal photos, and medical documents are all shared in the cloud. These are not just files. To a malicious actor, they're assets. They can be sold, exploited, or used for fraud. And once a data breach occurs, the damage is done. You can't just unleak your stolen data. That's why it's critical to prevent these breaches before they happen.
As we have seen, cloud data breaches can have serious consequences. And as cloud adoption continues to expand, security remains a pressing concern. In fact, according to a recent Oracle survey, the majority of companies have reported data security as their #1 concern for cloud. Clearly, as cloud reliance grows, so does the demand for stronger, more reliable security solutions in the cloud. As a result, the computational computing market is experiencing rapid growth and is projected to reach $160 billion by 2032. With the popularity of cloud services, there have been significant hardware-based attacks as a result of cloud systems being shared between users. To address these vulnerabilities and further secure users' data, hardware companies developed hardware-secure processors that are now used by cloud providers in their server systems. Our product is based on Intel's SGX platform, another major player in this space, and we believe this foundation positions us well to thrive in this rapidly growing market.
Our product is based on a white paper that describes a security method specific to AI applications, named Darknight. The system overview of Darknight is as follows. The client is on the left, which is you and your private data. The server or cloud provider system is shown in the middle, and the GPUs used for AI acceleration are shown on the right, which you want to borrow to run your AI model. The GPUs are a shared resource, so this presents a potential for other users to manipulate this shared hardware and extract your data. First, your private data is securely transferred to the server or cloud provider. To train or inference your AI model, the Darknight algorithm will encode your data using a key that is retained within a secure environment. The encoded data is then sent to GPUs for processing, along with your model. The key point is that the GPU will never see your raw data. The GPU will produce an output that is also encoded, and when that output returns to the secure environment, will be decoded based on the key that was used to encode the data. The GPU output can then be used within the secure environment, either to continue AI training or inferencing, or using nonlinear models for computation. What did we observe about the secure server environment that can be improved? The encode and decode operations that provide data confidentiality are matrix operations, which are better suited for accelerated hardware. Our product moves these operations to the network edge of the server system. This also offloads the work which would be done by the CPU's secure environment, and this allows the CPU to increase its performance for other tasks. Using the net FPGA or network hardware which already exists on current systems for encoding and decoding will increase throughput while maintaining security for your data. The encoding operation is based on matrix masking. The sensitive input data to be used with an AI model, such as images, are each multiplied by a unique randomized scalar. This operation is followed by an accumulation of all these images, including a noise matrix, which then produces a batch of noise matrices or an encoded set. It's important to note that the randomized scalars and noise matrix are retained and used for decoding later on. The encoded set is then sent to the GPU along with your AI model. The GPU performs its computations and returns an encoded output back to the secure environment without ever seeing the raw data.
For decoding, we take the model's output set, which is still encoded, and then we take the randomized scalar matrix from before and we use its inverse to do a multiplication. And this results in our decoded data set. So what happens if we don't do any of this? Well, the images are passed around from environment to environment between shared resources, and they're not encoded at all, which means anyone can just observe them who has access to the shared resource. Now, what about our design? We're implementing our encoding and decoding on a net FPGA, which acts as a router between different server nodes, and within each server node, we have our trusted execution environment marked by the yellow. Notice that the GPU is not a part of the trusted environment, either because it's a shared resource or it just doesn't support that level of security. So, if we want to securely route, we must first place the data onto the FPGA, where it's then encoded, and then it can be sent outside of our trusted environment securely, either to another TEE, or to a GPU, or between GPUs via RDMA. And once it comes back into the trusted environment, we can decode the data and send it to the CPU. And we can scale this design by copying and pasting each node until we have a server rack that looks like this. So here's the architecture of our accelerator. It's 7 stages, so it seems a bit complex, but really it's not. It's rather simple actually. So to start, we have the IF stage that has instruction memory. So you need to load the program into here, and we have an API to do it. It really just is telling the processor which pixel of your images to load at any given time. Then you also need to load your image data into DMEM and your scalar matrix data. And once you've done both of these, then you can enable the pipeline and start the processing. So that takes us to our floating point units. We needed to break up both of them, multiplication and addition, into 2 stages each to meet the 8 nanosecond clock period. So first we have integer multiplication, and then we have normalization. Then we do integer addition, and then we normalize that as well. And since we've made these into 2 stages each, the feedback for the accumulator now spans 2 stages, which means to do this without some extra stalls, we need to interleave instructions, which again our API will do automatically when you generate those instructions. We also have a mux here to reset the accumulator when any given MAC operation is done. And then once the entire output image has been generated, we can send that data out. So say we have a CPU and a GPU and we want to send some data between them. Well, we can do it, it's just not secure. So instead, we should get rid of this link, and then we can add in our accelerator. And first thing to do is program the instruction memory. Now, our ARM compatible CPU will have a special instruction to go with the ISA that does this in one go. And then we also need to program the data memory, both the scalar matrix and the image data. So we'll have another instruction that essentially tells the processor we want to encode the data that we're sending out. So we do this, notice that the header and tail data are preserved, and the actual data of the packet itself is encoded and then sent to the GPU. Now, from the perspective of the rest of the network, the CPU and the GPU, this accelerator is just a FIFO. We have image data coming in, and then image data coming back out. We've also developed a simple API which will compile a binary that can then be placed onto the net FPGA inside of memory along with the image data, and then these are passed to the accelerator for processing. So a typical user doesn't have to concern themselves with the inner workings of the actual hardware, and we believe that by making this product as accessible as possible, it will become widely adopted. So we'll start by showcasing our API. To use it, you just import the generate binary function, then you specify the size of your images, the batch size, and the directory where the images can be found. If you run this, it will generate a bunch of text files for you. To display the images that we'll be processing in this demo, it's these. They're just 7 8x8 images plus a noise image. So now we're on the FPGA. I've gone ahead and copied over the text files that we just generated for the memories. So we can configure that just by using config mem and then specifying the text files. So let's do that. Now that that's finished, we can just execute by typing the execute command and specifying an output file. Let's also decode the data that we just encoded. We can take the encoded data that we just saved to a file and load that back into our batch, since now we want to decode it. We just execute and save to dmem decoded.txt. So now we're back in our demo environment. I copied over these encoded and decoded text files. In this file, we just have some scripts to convert these text files back to PNG so that we can visualize what the FPGA just did to these images. So here's our encoded data. It's pretty difficult to pull anything out of this. It's just noise. And here's our decoded data. So you can see that it completely recovered all of the images with zero error. So far, our demo has been pretty small scale, but we're confident that we can scale this up to more realistic images and applications. So we wanted to provide a software demo to show what this may look like. So here we have 7 images plus a noise image. Each one is 1024 by 1024 pixels, so pretty realistic size, and they're all in color. So what we do is we actually break these up into 3 individual color channels. So here's red, here's green, here's blue. So then we take each individual channel and we actually encode each one, and then we reconstruct the image at the output. So here are all the encoded images, and you can see it's pretty difficult to pull something out. You can maybe see some shapes, but you really can't make anything out. Now, we repeat the process to decode, and we fully recover our images with 0 errors. So we wanted to demo this to show the capabilities of our design with the promise that going forward we will deliver this in hardware. So what about performance? Comparing our accelerator to a software implementation on a baseline CPU, we have about a 4 times speed up. Our accelerator processes 1 floating point operation per cycle, whereas a normal CPU needs about 4 cycles to do the same. And you can see from the snail that this difference is quite substantial.
Our business model primarily consists of licensing IPs to mid-sized cloud providers and AI companies that can't afford the high cost of confidential computing solutions from the major vendors. Our product is designed for easy integration into existing cloud network infrastructure, offering strong security with negligible performance loss. We also plan to introduce optional subscription-based service for updates, analytics, and remote management, creating a steady stream of recurring revenue while expanding long-term customer value.
Wait, so somebody drained all my bank accounts? I wonder if that's because I uploaded my checks to the cloud?
Did you not encode them first? I encode everything, from my personal photos to my financial records. Hackers want that stuff. They can steal it and exploit it. This is our team. Alex is the leader of hardware development, Simon is the leader of software development, and Tim leads the FPGA implementation team.